There are a number of problems or methods where we might be interested in the sign of a function along trajectories. Say we have a function k of x comma y. When might we want to know its sign along trajectories? In a conservative system, we would have a function so that the change in time along trajectories would be 0. And for us to consider a system conservative, that function needs to be non-trivial. It needs to kind of not have constant regions. But that's one time that we would care about checking the sign of the derivative of a function along trajectories. We might be thinking about whether a system is conservative. And if that's what we're thinking about, then we're looking for a 0 in the change in the function along trajectories, because if the change in time of the function as we move along a trajectory is 0, that means the function is staying constant along a trajectory. I could also use the change in a function along a trajectory to rule out a closed orbit. If I had a closed orbit, okay, I start at some place and my function k has some value. Well, in a closed orbit, I eventually come back to that same spot, and so my function would have to come back to that same value. So if I'm on a trajectory where I know that my function is always increasing, I know that trajectory is not a closed orbit. If I'm on a trajectory where my function is always decreasing, I also know that trajectory is not a closed orbit. We saw one more argument where we wanted to look at how a function changed in time along a trajectory. And this was a system that wasn't conservative, but that we suspected had a closed orbit. And so what we found was that there was only one special trajectory in the system on which we weren't looking at the change itself, but we looked at trying to bring back the pen tool. We looked at the integral of this function as we went around a single period of the system. And we thought that we had a periodic orbit, and so we were looking for this is equal to the change in the function from our starting point to our ending point. And we wanted that change in the function to be 0, because if we're on a periodic orbit, we start with the function at some value, and if we come back, that function will have the same value. And so we looked at an argument in the weakly nonlinear van der Pol oscillator where we were searching for a particular special trajectory on which delta k would be equal to 0. And so this meant that dk dt was sometimes positive and sometimes negative in a way that exactly balanced out as we went around the trajectory, leading to a change in the function that was equal to 0. And in that one system, in that special case that we explored of the weakly nonlinear van der Pol, that happened to correspond to a single closed orbit in the system. So those are the 3 places that we've seen arguments that rely on looking at how a function changes along a trajectory. Let's look at an example where we're going to find dk dt along different trajectories of a system. How do we compute dk dt? We can use the multivariable calculus chain rule. We know that k depends on x, and x depends on t. We know that k depends on y, and y depends on t. So k is going to change in time, because when time changes, x changes, which then changes k, and when time changes, y changes, which then changes k. And that exact dependence is the partial of k with respect to x dx dt plus the partial of k with respect to y dy dt. So however much x changes with a change in time, the rate of change of x with a change in time, times the rate of change in k with a change in x, gives us the rate of change in k with a change in time due to the fact that x changes. And then we also have some change in k due to the fact that y changed with time, and so we add those together to learn how k is changing with time. We can find the partial of k with respect to x. It looks like it's negative 2xy, and then we have an x dot here. And then we can find the partial of k with respect to y. It looks like it's 2y minus x squared. and we have a y dot here. So we've plugged in the information that we had from the original function k, finding its partial with respect to x, and finding its partial with respect to y. That's the function, but we haven't thought about the fact that we want to be moving along a trajectory in our phase space. Well, along trajectories, dx dt is given by this function, and along trajectories, dy dt is given by this function. So we're going to do a substitution of dx dt along trajectories for dx dt, and dy dt along trajectories for dy dt, because we're specifically thinking about dk dt when we're moving along trajectories in our phase space. So I have dk dt equal to negative 2xy times x squared plus y cubed plus 2y minus x squared times x minus 2y. And then maybe I'll multiply this all out. So I have a negative 2x cubed y minus 2x y to the fourth plus 2xy minus 4y squared minus x cubed plus 2x squared y. Often I want to reason about the sign of dk dt, because if a quantity is conserved, if k were conserved along trajectories, k wouldn't change as I moved along a trajectory, so dk dt along a trajectory would be 0. I think it's pretty clear from looking at this expression, nothing here is canceling out. This is not 0. Okay, well then I might be interested in, is dk dt always positive? Yeah, it doesn't look to me like this is going to always be positive. Is it always negative? This doesn't look to me like it's going to always be negative. Okay, it looks like we might not be able to learn very much from this dk dt, but let's see what we can reason out about the sign. Terms that have a pure sign, like negative 4y squared, for any value of y, that is negative. So I'm going to put that out front. Oh wait, that's like my only term in this whole thing that has a pure sign in that way. Because like negative x cubed switches signs as x switches signs, plus 2x squared y switches signs when y changes signs, plus 2xy changes signs with both x and y, minus 2xy to the fourth changes signs when x changes signs, and minus 2x cubed y changes signs when both x and y change signs. So, okay, this quantity wasn't conserved, and it doesn't look like we're learning very much from thinking about how this quantity changes along trajectories, but we've seen an example of the method. What was the method? Given a function, k of x comma y, where we were told what dx dt is along trajectories, and we were told what dy dt is along trajectories, if we wanted to find dk dt, then that was equal to the partial of k with respect to x, dx dt, plus the partial of k with respect to y, dy dt. And this is equal to, I'll denote that k sub x, and then x dot is f of x comma y along trajectories, plus k sub y, g of x comma y along trajectories. Or I suppose one might actually denote this dk dt equals k sub xf plus k sub y g. So this is the general case. The change in the function as we move in x times the change in x that happens with time as we move along a trajectory, plus the change of the function that happens with y, times the change in y that happens with time as we move along trajectories. If this comes out to 0, that would be relatively obvious. If it is going to always be positive on every single trajectory or always negative on every single trajectory, that might require a little bit more reasoning, looking for perfect squares within the expression or things like that.